We will start now. This is, I think, a very interesting presentation. I've never seen anyone else present on this subject. And so I hope that you find it interesting and that you learn some things that you may not have known before. Now, low voltage drives are ubiquitous. Everybody knows about them. Everybody uses them. They have a pretty good idea of how to use them, the problems that come from using them, and so forth. Medium voltage drives tend to be a little bit more cryptic because a lot of people don't have experience with them. But medium voltage drives are getting much more popular now. And so I think it's a good idea for you to be familiar with them. Now, the first thing you might think was, well, the difference between a low voltage drive and a medium voltage drive is the voltage. Not really. In my opinion, the difference between a low voltage drive and a medium voltage drive is about the same thing as the difference between a switchboard and a motor control center. I mean, they're very, very different, and that might be surprising to some. In many applications, you could select either a low voltage or a medium voltage drive, and so this presentation helps you in terms of making those kinds of decisions. So the first thing we ought to do is have some definitions. What is low voltage? What is medium voltage? There are a lot of different definitions for low voltage or high voltage. In some places, high voltage might be 120 volts. In our case, we're using ANSI standard C84.1 that identifies low voltage as 1,000 voltages less, and medium voltage as greater than 1,000 but less than 100,000. So in terms of medium voltage, we're going to typically use drives that are 2,400 volts, 4,160 volts, or 6,900 volts, whereas low voltage drives typically are 208, 240, or 480 volts. Now, let's talk first about the complexity. Would you say that a low voltage drive is more or less complex than a medium voltage drive? Well, I think that's kind of an easy one. If you look up in the upper right, there's a little box that says advantage. I have added that box throughout this presentation, and that's my opinion, and you're welcome to have a different opinion, but that's my opinion as to which one has the advantage. And you notice there's a check mark in the low voltage, and that means, in my opinion, low voltage drives are less complex and therefore they have the advantage. However, this may be misleading because there are other factors when you use low voltage drives that don't necessarily apply to medium voltage drives, such as harmonics, leading power factor, motor insulation, motor bearing currents, and so on and so forth, which we will get into in this presentation. Next, let's look at the qualifications of the service technicians, which would require more highly trained service technicians. Well, there again, I think the advantage goes to low voltage. We have a lot of service technicians who are familiar with low voltage, and because most low voltage drives are roughly the same, then they can go from one drive to the next. Now, by roughly the same, I'm not trying to say that a Mercedes is the same car as a Yugo, but what I mean by the same is they have internal combustion engines, they have spark plugs, they have the same cycles of bringing in fuel and so on. So low voltage drives are typically built in a similar fashion, have been done since the Japanese introduced this technology in about 1987. Medium voltage drives, however, are still widely different from one another, and they use a number of different technologies. So not only does someone need to be familiar with medium voltage, be familiar with medium voltage drives, but in many cases, to have someone work on your medium voltage drive, you're really going to want someone with training and experience on their particular brand and model of medium voltage drive. Physical size, which one's bigger? Well, here, I have actually given the advantage to both. And that depends upon what you have to have there. For instance, here's a low voltage drive on the left. We have an active converter on that one and a medium voltage drive on the right. But if you have to have harmonic filters, sine wave output filters, step down transformers, it is very possible that a medium voltage drive could be smaller than a low voltage. But in most cases, medium voltage drives are certainly going to have a significant footprint. How about cost? Which costs less, a medium voltage drive or a low voltage drive? Now we're going to spend a little time here because this is the crux of a lot of the decision making that will have to go on. So let's start on the top line. On that top line, we have a utility. It goes straight to a drive and then to a motor. So let's say you have a small facility, you get 480 volts from the utility, it goes to a 480 volt drive to a 480 volt motor. That is typically going to be your lowest cost up through about 1,000 horsepower or so. But where do you get the 480 volt from? Well, typically you're going to have to step it down. Utilities don't have transmission and distribution systems at 480 volts. So either you will have to step it down or the utility is going to have to step it down. And when you add that transformer, you are increasing the cost as well as the footprint. Now, in larger facilities, that transformer is going to be a part of your distribution system. So you're going to have to find a place to put it. Where medium voltage drives can take power generally directly from the utility at 4160 volts, at 12470 volts. We'll use 12470 as an example because that's a pretty common utility transmission distribution voltage. I should say distribution. And if you do that, you really have to add the cost of that transformer, the pad, the mounting, the cabling, the relays, the protection, fuses, circuit breakers, so on. You're going to have to add all that to the cost of your system. And even if you have a small system in which the utility might be providing you power at 480 volts, if the majority of your power is the drive, then don't get that transformer or get a very small transformer, and that tends to affect the cost. Now, we're assuming that you have a 480 volt motor. What if the motor is 4160? Well, now, if it's an existing 4160 volt motor, you have to step the voltage down, you have to go through a 40 volt drive, then you have to step the voltage up. And in so doing, in either line 2 or line 3, you're almost always going to have harmonic filters. I can't even remember the last, multi-hundred horsepower drive of any size that we put in without a harmonic filter. So you really need to add the harmonic filter to the cost. And then in line 3 there, where you have a step-up transformer, we highly recommend that you put an output filter, typically a sine wave filter, in order to filter the drive to protect that transformer, because you very well may have a high rate of transformer failure because of the PWM waveform going to the transformer. And finally, line 4, again, we're back to the simplicity of one drive and no transformers. And so in this case, let's say you have 12470, you come in with 12470, you go out with 4160 and go straight to your 4160 volt motor. You'll notice that that drive has a isolation transformer built into the drive. We highly recommend that you have that. I wouldn't want to purchase a drive that didn't have an isolation transformer built in. And if you do that, then your input voltage and your output voltage can be different. And that's something that is not the case with low voltage. So cost will depend upon all of those factors. Is the motor existing or new? How large is it? The conduits can make a difference. You've got an 800 horsepower motor, you've got a lot of amps, you've got a lot of cable. And so any significant distance, that medium voltage drive can certainly save you in cabling, and that can affect your conduits and your distribution throughout. So could be either. Efficiency. Which one would you say is more efficient? Well, I've given the advantage to medium voltage here. Now, if you go look at a medium voltage drive cut sheet, and then you go and look at a low voltage drive cut sheet, you will find that the medium voltage drive is actually less efficient than the low voltage. But I think that's misleading. First of all, a 40 volt drive has to get power from someplace, and that means you're going to have a step down transformer, and that transformer has losses in it. So that transformer is included in the medium voltage drive. It's not included in the low voltage drive. And let's say that's 1% efficiency. That is not on the medium voltage drive cut sheet, or excuse me, the efficiency of the transformer is included in the medium voltage drive cut sheet, not in the low voltage. So you really have to factor that in because those are legitimate losses. Next, because low voltage drives tend to have poor harmonics, you generally are always going to need a harmonic filter of some sort, and that is going to add losses to the system. And finally, the poor output voltage waveform on low voltage drives is going to tend to increase your motor losses, so that's something else to consider, and those additional losses are not going to show up on the low voltage drive cut sheet. So I'm going to give the advantage to medium voltage drives there. How about safety? Which is safer, a low voltage drive or a medium voltage drive? Well, I give the clear advantage to medium voltage drive here. Now that may be a little bit surprising if you haven't worked on these things. You may say, how can a 4160 volt drive be safer than a 480 volt drive? Well, let's talk about that. Here's a 480 volt drive. In order to put that drive into service, you're going to have to go in, you're going to open the door, you're going to energize the drive, you're going to measure the voltage on the circuit breaker coming in on the drive, voltage from A to B, voltage from B to C, voltage from A to C. You're going to measure the voltage on that capacitor there if it has a harmonic filter, and so on. And when you do that, you put yourself at risk for arc flash. And most of you hopefully are somewhat familiar with arc flash. Arc flashes are burns and they're really scary. So I decided to include a couple of short videos that I think will illustrate this. Now, this is a 480 volt piece of equipment. It is intentionally, we've got some wires short circuiting that thing. So when we energize it, it is going to have a short circuit. And that's what it looks like. Now, that's scary enough, but let's take a look at it in slow motion. This is a different piece of equipment, but this piece of equipment is also 480 volts. The person standing in front of the equipment is a mannequin, so we are not doing this to a real person. The mannequin is tied off, so it can't move. And in slow motion, this is what an arc flash looked like. Now the fire there is 35,000 degrees. That's 3.5 times hotter than the surface of the sun. It will give you third-degree burns virtually instantaneously. And you can see that that poor mannequin there is surrounded with fire. So this is kind of a big deal to me. And anytime you open the door to a 480 volt cabinet, you subject yourselves to that possibility. So whenever we work on 480 volts, we've got to have arc flash protection. And here's some people on the right that are all dressed up in their arc flash protection. You've got to have arc rated shirt and pants or arc rated coveralls, and you've got to have an arc rated face shield. And with all that, you still may be subject to an explosion. And so that is, anytime you work on 480 volt energized, it's a concern. In addition, medium voltage drives have major safety enhancements. The biggest one that I'm going to point out there is that the major faults remove permissives and drop power to the drive. Every drive that we put in, we insist on having something upstream that is not a switch. It could be either a fuse switch, or excuse me, not a fuse switch. It has to be a circuit breaker of some sort, or a fuse switch and a contactor, so that if the drive senses a fault, and they have lots of sensors in there, then it will immediately trip that contactor or trip the circuit breaker. And that could just be the distribution circuit breaker coming in to the drive, and it drops power to the entire drive. So that makes it safer. But the thing that mostly makes it safer is bullet point 4 down there. That's your Kirk key interlocks. So here is a typical drive. This is a TM-MVe2 drive. TMIC is Toshiba, Mitsubishi, and GE. They formed a common company there. And that's what the outside looks like. But when you look at the inside, this is what it looks like. Over here on the left, we have our transformer. Here's our contactor, excuse me. And here's your converters and inverter modules. You never, ever, ever get into any of these areas while that drive is energized. And in fact, you have to lock that drive out, then get Kirk key interlocks in order to open the door. So guess what? If it's de-energized and locked out, you don't have that same concern that you do on a low voltage drive. On a medium voltage drive, if you want to know, or on a low voltage drive, if you want to know the voltage coming into the drive, you open it up and you get out your meter and you put on your arc flash protection. On a medium voltage drive, you simply look on the keypad. You do not get expose yourself to a potential arc flash. Now, I have never known anyone who's been injured on a medium voltage drive. I know lots of people who have been injured working on low voltage drives. So that's an important point. I think when you're looking at choosing one or the other, safety should be a major point that you consider. Now let's talk about reliability. Which one would be most reliable? Well, here again, I give the big advantage to medium voltage. You look at that upper left, these are very common drives. They just grab them, mount them on the wall, and we find that lifespan of these drives is generally 3 to 7 years. Now that's not mean time between failure, that's lifespan. If you look at the drive on the lower right, this is more of an industrial high quality drive in which we put it in a metal enclosure and we have forced filtered ventilated so that it keeps everything inside very clean. You should get 20 years out of this drive. But I'm not saying 20 years of mean time between failure, I'm saying 20 years lifespan. The mean time between failure is not going to approach 20 years regardless of what supplier you use. Here again, I'm using TMIC as an example, but drives, very high quality drives like the TMIC drives have 15 to 40 years mean time between failure. They are much higher quality drives. Now, I was the director of engineering for Geneva Steel. When we had an outage on our plate mill, it cost us $100,000 an hour. Of course, that's pretty high, but I would say regardless of where you are, outages cost money, and therefore the mean time between failure is a big deal. We have sold lots of drives, and knock on wood, we've never had a medium voltage drive fail. And we sell mostly the TMIC drives, but that's pretty darn good. I wish we could say the same about low voltage drives. Motor insulation. Why is that an issue? Well, I give the advantage clearly here to medium voltage drives. Let's take a look at the output of a medium voltage drive. Look on the top, that's what's called a PWM waveform. And most of you are pretty familiar with the fact that drives don't put out a sine wave. Even if it's called a sine wave drive, it puts out a PWM pulsed signal. And most motors are VFD rated motors, can handle that. If you have long cable lengths or you've got a standard motor, then you may need to put something down here on the lower right. That's a DVDT filter, and that basically filters this output waveform and make sure that the voltage excursions do not go higher than the rated insulation of the motor. This slide's from TCI, Transcoil International. It's available right on the internet. It shows the output waveform with 70 feet of cable and with 500 feet of cable. If you're using a standard motor, it has 1,000 volt insulation, and you can see these spikes go above 1,000 volts. The spikes get worse with 500 feet of cable. So with long cable lengths, we many times have to put a filter on that low voltage drive. That has prompted the motor suppliers, who are part of National Electrical Manufacturers Association, to publish a standard MG1. Of course, MG1 was in effect long before VFDs came into effect, but they had motors and they had 1,000 volt insulation. When they started having more and more motor failures because of variable frequency drive, they added part 31 and added a special VFD rated motor, which has the standard says 3.1 times V rated, but it's approximately 1,600 volts of insulation. And I think most of you are familiar with the fact that anytime you buy a low voltage drive, you need to buy a VFD rated motor with VFD rated insulation. That is not the case with medium voltage. In fact, medium voltage motors, there is no standard medium voltage VFD rated motor. You have to look at the installation. So I'm going to explain to you a little bit what causes that. Down here is our 2/3 level inverter. Now in the industry, that's called a 2-level inverter, but I'm trying to be specific by calling it a 2/3. So you'll notice down here, if you go from 0 to peak, that's 2 levels. 0 is 1 level, the peak value is another level, so that's a 2 level. If you want to go peak to peak, then you'll notice that it has 3 levels, 1, 2, and 3. So we'll call that a 2-level inverter. All low voltage drives are 2-level inverters. And that's why you have the problem with those steep spikes that go from, let's say on a 40-volt drive, 0 voltage up to maybe 650 volts suddenly, and that can be very difficult on installation. Now, all low voltage drives are like that, but not all medium voltage drives are like that. Some are, but most are not. Here's a 3-level inverter. Notice we have two different DC buses, and now you have 3 levels. There's 0, half voltage, and full voltage, and that would give you 5 levels from peak to peak. That makes a world of difference on your motor installation. But wait, as they say on TV, it gets better. There is a 5-level inverter out there, and you can see now that you get 1, 2, 3, 4, 5 levels. We used to consider 5-level kind of state-of-the-art. That was like the best you could get. My opinions, a 3-level inverter is okay for 2400 volts, but in today's market, I wouldn't use a 3-level inverter. I would insist on 5 or more levels. So again, wait, it gets better. Here is a state-of-the-art drive. Again, this is a TM-MVe2. It has 9 levels. So that's 9 levels from 0 to peak, or 17 levels from peak to peak. Look over here. That's an actual waveform of the output voltage. And guess what? That is a sine wave. That's just as good as coming right off the utility. That gives you a perfect sine wave. You can't get that on a low voltage drive, but you do get it on a medium voltage drive, and that's an exciting thing. We had a wind tunnel once where the motor was suspended in the middle of the wind tunnel, and we had a motor quote, we had a drive quote, but every pound was important. We talked to the motor manufacturer and said, is there any way that you can reduce the weight of this motor? Well, that's kind of tough, but they said, well, show us your output voltage waveform on the drive. We showed them this waveform, and they said, oh man, that's like a sine wave. They took, and I think this was a 3,000 horsepower motor, they took 2,000 pounds out of that motor, and that was all insulation because of the output waveform. So those output waveforms can mean a lot, and it is not difficult to get a voltage waveform like this with the state-of-the-art manufacturers. But I would consider 5. There are still lots of drives out there, medium voltage, that will have like a 3-level output. I would get at least 5 levels, and if you get into something like this with 9 levels, that's a really amazing drive. EMI RFI, which do we give the advantage to? Again, I give the advantage to medium voltage. You look at the output waveform, one has all these spikes, the other one is a virtual sine wave. I think that kind of speaks for itself. Now, on low voltage drives, more and more motor manufacturers and drive manufacturers and motor repair shops like ESA's, the Electrical Apparatus Service Association, they recommend that anytime you have a VFD that you use special VFD cable to go between the VFD and the motor. Now that special VFD cable looks like this in its best version. So you have your 3 conductors all symmetrical in a cable. Then we have 3 grounds, not 1 ground, but those 3 grounds keep the ground voltages symmetrical. And then around the outside, you have an overall shield of armor. We're not going to get into lots of details on that, but suffice it to say that this is becoming more popular and more recognized. This increases the cost of your cabling, especially if you get into multiple hundreds of horsepower, and you might end up on a low voltage drive with multiple conductors per phase. This is a very interesting table. And let me just point out that here's an open tray with individual conductors, 3 conductor unshielded with 1 ground, 3 conductor shielded with 1 non-centered ground, so we're adding the shield, and then 3 conductor shielded with 3 symmetrical grounds. And you can see in terms of EMI propagation or bearing currents that you have poor, you have better, and you have good. So we tend to recommend bearing protection in the form of a insulated bearing or a grounding ring, but the better the waveform, the less bearing problems you have, and this definitely reduces the problem with bearing currents. But more, we're concerned about the insulation. So here's a 2-level drive, and on 2-level drive, this is all low voltage and some medium voltage. They say not recommended for open cable tray, not recommended for 3 conductor unshielded with 1 ground. 3 conductor with 1 non-centered ground and a shield is marginally acceptable. And so they're recommending as a minimum, really, if you want to be good, if you want to be in that good column, get yourself that VFD cable that has 3 conductors, 3 grounds, and a shield. If you go with a 3-level drive, and you remember we went with 3 levels, and NPC is neutral point, which a lot of drives have, then open cable trays, this is actually marginally acceptable. It's not acceptable to me, but the manufacturer, and this is T-Mic, says that's marginally acceptable. When you get into these other 3, then it's acceptable and good because of the fact that the waveform is so superior. All right, displacement power factor. So most variable frequency drives have excellent power factor, and I really think that medium voltage drives and low voltage drives both have excellent power factor. Low voltage drives about, well, above 95% displacement power factor, all of them. Medium voltage drives, other than the current source drives, pretty much all of them over 95%, and some are even better than that. So this is our analysis. This is a very common metaphor of the beer. So you have beer, and then you have foam, and then you have your apparent beer. Well, power factor is the same. You've got your useful work, which is watts, your wasted capacity, which is VARs, and your kVA. So the better the power factor, the more watts you have for a given kVA. And those watts, of course, go out throughout your plant. They cause the current to be higher. They increase heating in your transformer, and you may end up with a utility penalty for low power factor. Fortunately, all drives are pretty good at that. Now let's take a look at harmonics and power quality. Here we have a phenomenal difference, and medium voltage blows low voltage out of the water. Now, a lot of low voltage drives are advertising less than 5% total harmonic current distortion. When we get them in the field and we actually measure them, very few of them actually live up to that. In fact, there's only 1 drive that we would guarantee would give you 5% power factor, or excuse me, harmonics, and even that one only works at higher loads. By contrast, this again is the medium voltage drive that we've been talking about. If you look in the lower left-hand corner, I told you that most drives are over 95% power factor. This has 100% power factor. And in fact, you can even tell this drive to produce leading bars if you want, and actually correct power factor in the rest of your power distribution system. Amazing. But it also has 2% total harmonic current distortion down here. That's phenomenal. You cannot match that with a low voltage drive regardless of what technology you use. Why is that? It's because they can use phase multiplication in series rather than in parallel, and the active converters have multiple converters, so you just get incredible performance. How about low voltage? Well, there's a sine wave. Anytime you put a drive on there, you do not get a sine wave. You get pulses of current in to charge the capacitor on the variable frequency drive. And that's the typical waveform of a low voltage variable frequency drive. That waveform's kind of bad. And that particular waveform will generate very high levels of harmonics, about 100% on a typical drive. It can cause all kinds of effects due to the harmonics, and I'm not going to go through all those effects. Suffice it to say that harmonics means you've got high frequency currents on your distribution system, and they will cause problems. They may not cause problems that prevent you from operating, but it's certainly not as good as a sine wave. This is my little bad neighbor theory that basically says there's two kinds of bad neighbors. One kind of bad neighbor is the kind of neighbor that plays Led Zeppelin at full blast at 2 a.m. when you're trying to sleep, and you need to get up early in the morning. But the other kind of bad neighbor is the guy who calls the cops on you when you're playing Led Zeppelin at 2 a.m. I think this has application to power distribution systems. One kind of bad neighbor might be the drives, which create high frequency noise. The other kind of bad neighbor might be the devices that act up or fail or have problems, such as your communication system. Sorry, I had to click off that window. So in most cases, you want to limit the noise on your system. Why? Partially for your system, but partially because that noise is going to go to the utility, and utilities have standards, which we'll talk about in just a minute. Harmonics are basically just pollution on the utility system. Now, this is a standard drive. This is standard with all manufacturers of drives. You got a converter, you got a DC drive, and you've got your DC to AC inverter. Your total harmonic current distortion on the bottom is 70, 80, 90, 100%. And so that's pretty bad. That means for every amp of current going to the motor, you have like another amp of high frequency noise being generated on your power distribution system. I'm going to go through various ways in which we compensate for that with low voltage drives, but I'll do that pretty quickly. So the first is line reactors. Love line reactors, and they will actually limit your current distortion down to 30 to 40%. That means you eliminate 2/3 of the distortion. They're cheap, they're easy, they can be used on any variable frequency drive. And I'm always preaching that. Here is without reactors. Here's the waveform with reactors. Now, I'm not saying that's a sine wave. It's not like it's great, but this is 100% distortion. This is about 30% distortion. If you put either line reactors or good quality DC link reactors, they have to be at least 3%. You're going to get 30, 35% distortion. And so that's a lot better than 100%. This is a 12 pulse drive. It uses 2 converters on the front end. You can get down to 12 to 20% distortion. This is a pseudo 12 pulse, same distortion. Here's an 18 pulse drive. Now you have to have 3 converters. Obviously, we're really increasing cost here. And you have to have a phase shifting transformer. I should mention that's also the case on a 12 pulse drive. You have to have phase shifting transformers in front of the drive in order to get these multiple converters to share load equally. This is a hybrid filter. This is by far the most popular way of correcting, because you get total harmonic current distortion, really down between 4 and 15%. What we typically see is 7 to 8% total harmonic current distortion when applied in the field. And most manufacturers now of hybrid filters have a filter that they're saying is less than 5%. And we have purchased a lot of those. I've never seen one be less than 5%. This is an active front end. One manufacturer is producing this. They're claiming it's under 5%, but it can only go up to 88% voltage. Anytime you go over 88% voltage, then you cannot be in low harmonic mode, and you'll typically be up around 12 or 13%. This is the pièce de résistance, or the the Cadillac or the Mercedes. This is your active bridge. And even on an unbalanced system, that active bridge at full load, you can get about 2.5% distortion, but that's only at full load. Once you're about half load, you're going to be around 5%, and below that, it gets worse. It's a great technology, very costly. And finally, we have active filters on the bus. These actually can get you below 5%. In this case, you would put line reactors on your variable frequency drives, and then you would apply an active filter on the bus to clean up the remainder of the harmonics. They work a little bit like noise cancellation headphones, and they're getting to be very, very popular. They work very well. As they get more popular, the price is coming down. As the price comes down, they get more popular. So that's a good technology as well. And this is a little diagram of how they work. They basically are noise generators that generate noise 180 degrees out of phase with the noise generated by the drive, and therefore they correct. But they only correct at the point where you apply that active harmonic filter. But some really nice technology there. But guess why all of that technology is necessary? All of that technology is necessary because low voltage drives have very poor harmonic performance. And therefore, there are various types of technologies in order to clean that up. You don't need any of those technologies with a really quality medium voltage drives because it doesn't generate those levels of harmonics. And therefore, you don't need any of these technologies. The drive is clean. In fact, that drive I showed you earlier had 2% total harmonic distortion. That's less than or equal to an across-the-line motor. Even if you have an across-the-line motor, it's going to have some harmonics. So I like to say that's just like an across-the-line motor. It's like a light bulb. These good medium voltage drives are clean power, and you do not need to worry about it. So here's a comparison of the different methods that we have talked about. And this is IEEE 519. A lot of people think IEEE 519 means you have to have 5% distortion. That's not true. You can have between 5 and 20% distortion depending upon the size of your load and the size of the utility that feeds it. In almost all cases, we find that you have to get to 12 or 15%. And so 12% is a good place to aim for. And that's good because even these technologies that advertise less than 5%, most of them do not deliver. This is a utility standard, and the utility can hold you to this and can can limit your service if you don't comply with that. I want to talk about some complications very quickly. And here's a 12 pulse. You can see that at full load with very little voltage unbalance performs pretty well. But as you get lower in load, and if you have some voltage unbalance in the system, and we all do, the harmonics get worse. This is an 18 pulse, kind of looks the same. Why do we get worse at low voltages? Because we're trying to balance those three bridges. This is a hybrid filter, and this again gives you your best performance for the price. And you can see much better behaved, but still typically isn't under 5%, but it's well under 12%, which is where you really need to be. This is your active bridge, and this is the best. You'll notice that this is on a highly unbalanced system. In our shop, where we measured this, you're down here about 2.5% distortion. Fantastic. But as you lower the load, then that performs less well because the harmonics in an active bridge are generally the same regardless of load. Now, miscellaneous things, and we're just about done here. Number one, low voltage motor cables must be sized at 125% of full load amps. That's a National Electrical Code provision. Medium voltage motor cables don't. The standard basically says that on medium voltage cables, you size the cable at wherever the medium voltage drive is programmed to trip. And therefore, they're leaving that up to the engineer to set that drive and the cable appropriately. So for long cabled runs, you can significantly reduce the amount of cable. Medium voltage drives with isolation transformers allow the drive input voltage to match the utility or plant distribution system, while the output voltage can be matched to the motor. And with proper selection, you simply never have a power quality problem. You don't have VARs, you don't have poor power factor, and you don't have harmonics. It's just all taken care of for you, and it's something you don't need to worry about. With some medium voltage drives, you can actually have regenerative power, Or, as I mentioned before, you can program that drive actually to provide leading bars to correct for lagging bars in the rest of your power system. Finally, low voltage drives can excite system resonances if power factor capacitors are used. Medium voltage drives typically don't have that problem. So you might figure that throughout this presentation, I like medium voltage drives, and you would be correct. I'm always going to try to go with a medium voltage drive if I feel like I can justify the cost. When you are looking at the cost, remember to evaluate the efficiency, look at step-down transformers that you may have to add, look at cabling, and then consider the effect of insulation on your motor, of power factor, of harmonics, and factor that into your choice of either medium voltage or low voltage. And finally, of course, reliability is a huge deal. Medium voltage drives are vastly more reliable than low voltage drives if you get the right drive. It has to be a real heavy duty systems drive, but that doesn't come at a cost premium. They have excellent drives that provide all of that. So remember, not all medium voltage drives have the advantages mentioned in this previous presentation. Some, especially older designs, are not as good. There are still people coming out with 3-level drives that I wouldn't probably use on 4160 volt. But medium voltage drives can be fantastic. Certainly consider them when you are evaluating your larger drives, or your larger motors and your larger motor applications. So that's all. I'd like to open it up for some questions, and maybe Tyler can, if there are questions, can read those off for us.
Yeah, absolutely. Feel free to send in more, but we do have one just to start off from Dave. Going back to the levels, what he said is, what is the highest level inverter available and what type of harmonics does it reflect?
Well, the harmonics generally are 2%, is about as good as it gets, but like I say, that's like a sine wave. And there are lots of drives that give you that. You can get that either from an active front end drive, which we like, or from a multi-pulse converter. Now, the multi-pulse converter, I would suggest that you use a minimum of 24 pulse, and some manufacturers are going to 12 or 18 pulse. But if you get a 24 pulse converter, it's basically clean power. It's as good as an across the line motor. The other thing had to do with levels. Levels will depend upon your voltage. So the higher the voltage, the more levels you get. And you can get at higher voltages, 13, 15, 17 levels, and even more than that between 0 and peak. Once you get to 9 levels, boy, you have pretty much a sine wave, and more levels than that, you don't really get any advantage. So I would say at 2300 volt, 3 levels is okay, and I wouldn't have a problem buying that. At 4160, I would have minimum of 5, but if you could get 9 or above, then you are golden. There really aren't any advantages above 9 levels.